In this video, I'll be reviewing problem 1, Andrew's idea from the hockey homework document. And so we'll go through that, starting with some of the key information that we had at the top. So as I've shown on the whiteboard here, we've got that the mass of each crate is 55 kilograms, and we also know that the gravitational acceleration is 9.8 meters per second squared, shown with a negative sign there because this is a downward acceleration. And so it should be shown in the negative direction because generally we have positive direction as being up when we're talking about vertical. So what we need to know from this first off is the weight. And one thing we know about weight is that weight is a force. We can calculate it very similar to how we find a normal force. We just take mass times the acceleration, and in this case the acceleration is that gravitational acceleration that I showed on the left, the negative 9.8 meters per second squared. Plugging that in, we're going to get 55 kilograms times negative 9.8 meters per second squared. And that'll come out to about 539 newtons, which when we round it for significant figures, it's going to go to 540. 540 newtons being shown with 2 sig figs there because the 55 has 2 sig figs and the negative 9.8 also has 2 sig figs, so our answer should have 2 sig figs. Should also include that it is negative here, but generally when we talk about weights we give the magnitude, the size, so we don't worry about the negative sign. Usually we would just say that the weight is 540 newtons, and it would be understood that we're talking about a downward force there. So this is going to be necessary for some of the later stuff, but first thing we have to do is just to draw a force diagram to represent the forces acting on our crate. We're just worried about the horizontal stuff, so we don't have to worry about anything else for the moment. And as a reminder, this situation is the one where we are putting the two crates separately, so just one at a time. We can make a little bit of a diagram to show what's going on here. So we've got the crate over there, and we've got our hockey team person over here pushing it, in this case pushing it to the right. To make a force diagram, I'm going to just make another part off to the side here. I usually represent them as boxes, but you can draw any little shape over there. And so we're going to show what forces are acting on this. As we said before, we've got a push going to the right. The person is pushing it to the right, and so that's going to exert some force on it. And so we'll draw this and then label it the push. We also know that the box is in contact with the ice, and because of that, the ice is going to exert a friction force on the box to prevent its motion, or try to prevent its motion. So because we've got this box going off into the right direction, the friction force is going to go to the left. And so we'll draw that as friction. For now, we're not so much concerned with the magnitudes. This will actually change depending on which part of the problem we're dealing with. And so we will just consider this to be showing that the push is going to the right, the friction is going to the left. We will not worry about the size of the arrows for now. We'd also want to think about whether any other forces are acting on the crate in a horizontal direction, and we really don't have anything else that can do that. Only the person and the ice are in contact with the box. We also know that gravity, one of the forces that we know does not require touch, it's acting vertically, and since we only are concerned with horizontal stuff, we won't need to worry about that. So this should take care of what we've got for our force diagram for part A. We then need to figure out the push force that's required for the first 5 seconds when the box is accelerating at 0.20 meters per second squared. So the key thing for this is that we know that the box is accelerating. What this tells us is that there will be some net force acting on the box, and we need to include that. So in order to do that, we're going to have to set up a calculation using Newton's second law of motion, which tells us that net force equals mass times acceleration. We already know the mass. This was given to us that the mass of the crate is 55 kilograms. We're only dealing with 1. And so that's all that we'll put in there. And we know the acceleration. We know the acceleration is 0.20 meters per second squared because the problem tells us that the crate is accelerating at that rate. To solve this, we just do that multiplication. It'll come out to 11 newtons, which is already shown with proper number of significant figures. The 55 has 2 significant figures. The 0.20 has 2 significant figures because only the second 0 is significant, which means that our answer should also have 2 significant figures. So this tells us that we have a net force going to the right, our positive direction, and it is 11 newtons strong. We can add this to our force diagram as a net force, and so this 11 newton is our net force, shown in a different color to show that it's not just one of the component forces. We're also going to have to figure out some information about the other forces. So the component forces acting here, the push and the friction. The document told us that we can assume friction is going to be equal to 1/10 of the weight. This means for us that since the weight was 540 newtons, again, since I'm talking about a weight, I'm going to just give the magnitude as 540. We know it's going in the down direction, so the force itself is negative 540. But since its weight is 540 newtons, we're going to take 1/10 of that. And so we can show this as a condition as friction equals 1/10 times weight. Generally, when we see of in a mathematical context, that implies multiplication. So 1/10 of the weight means we multiply those together. So we're multiplying 1/10 by 540 newtons to end up with 54 newtons. We can now return up to the diagram that we have, our free body diagram, and show that this is going to be a 54 newton friction force. We can also say that it's going to be negative, because as we can see, it's going in the negative direction. Generally, we define the right as the positive direction when we're talking about horizontal motion. That gives us two of the forces on this diagram, the net force and one of the individual forces. Using what we know about how net force is defined, we know that these two forces should somehow be related to the push force by an equation. If we put in that the push force is X, so some value there, we know that the two component forces here must add up to the net force, because by definition, the net force is what we get when we combine all of the individual forces acting on an object. We can now represent this in a calculation by adding those two forces, so X plus negative 54 newtons, and setting that equal to the net force. And in this case, our net force is 11 newtons. In order to solve from there, we'll need to get the X on its own, so this is algebra that we're using. We can do that by adding 54 newtons to both sides. This will get rid of the negative 54 newtons that's along with the X on the left at the moment. When we do that, we're going to end up with X equals now 65 newtons. And since this was our original push force, we'll go ahead and put that in as 65 newtons. This is what we're asked to find in the original question. We were asked to find that push force, and so that will be our answer for part B. That is the push force required for the first 5 seconds when the box is accelerating at that rate. So that'll take us through the first two parts of this problem. I'll go ahead and stop the video for there, but we'll continue in the next video with the following two parts.